and similarly for ln bars. The meaning of these things is that acting on any function, these are the generators. So, let me make it a little more precise. Suppose I have a field, I will call it chi z and z bar. This field is called a primaric field if under conformal transformations I get a new field Okay. So, let me explain what this thing means. H and H bar are called the conformal dimensions. So, just to get a feel for what this means, compare this with our discussion of normal field theories and calculations of dimensions of field just based on dimensional analysis of the action. Okay. Just to remind you, you have a field in d dimensions and the action is d phi whole square, and I said that the dimension of phi is given by d minus 2 by 2. What that really means, of course, is that if I scale x to lambda x, then phi should scale as lambda raised to the power d minus 2 by 2 phi. Or in other words, if this is I call x prime, so phi then goes phi prime of x prime is lambda raised to the power d minus 2 times phi of x. If I make this change and if I make this change, this action is invariant. That is what we mean by dimensions. Dimensions are the scale transformations. But then now you can see that H and H bar are exactly the analogues of dimensions under scalings of z and z bar, right. But a scaling of all the z's and z bars, uniform scalings of all and z's are, they should have the same factor for. So, under separate scalings of z and z bar, h and h bar are indeed dimensions. And in the same sense as this, in a more roundabout way of saying that if I make a renormalization group transformation on this thing, this is the factor it will pick up. Well, the fields are going to pick up. But what is called dilatations are z going to lambda z, but z bar also going to lambda z, and it is under dilatation. See, I took all the coordinates x and scaled by the same amount. That tells you that this object h plus h bar denotes the real scaling dimension of the field. This is clear because it is again the same factor, lambda to the power minus h, lambda to the power minus h bar. This is consistent with the fact that scale transformations are generated by L naught for just the scaling of z, L naught bar for just the scaling of z bar. So, if I want to scale all of them, you got to do L naught plus L naught bar. In a similar way, we found that L naught minus L naught bar gives you rotations in the plane. Sorry, L naught minus, yeah, that gives you rotations in the plane, right. So, what L naught minus L naught bar if I take the scaling of h minus h bar should correspond to the spin of the field. In two space dimensions, there is just one integer which is the spin, because there is just one rotation. So let us take this and figure out what is the variation of the field. It's a short exercise to show that the variation of this field gz bar, say under g prime equal to z minus epsilon of z minus, sorry, that's defined by chi prime of zz bar minus chi of zz bar. This is the way the function itself changes, that is the transformation of the field, and you can just calculate that this becomes so there are two pieces which come from from this non-trivial transformation property with h and h bar. There is one piece which comes from the factor which is sitting out here, and there is another piece which comes because I have to change z prime back to z using that formula, right. If there was a function which had h equal to h bar equal to 0, that's just a regular function which is called a primary field of 0 dimension, then you don't have this term, right, and then the generators were exactly those LNs. Or in other words, the action of, so if epsilon of z equal to z n plus 1, so del g phi, and you want to find an operator Ln which is a function of the field and its canonical conjugate momentum, which has the property that the commutator of this with, this is how transformations are done in quantum mechanics by commutators of charges. Such that the result of this commutation relation is just that, then clearly the algebra of these operators with capital Ln will be very similar to the algebra which is of those operators, except with a slight subtlety. It turns out that these operators satisfy an algebra this is called the Virasoro algebra with a central extension, with a central charge. If you calculate what this operator is for the free scalar, massless scalar field theory in 2 dimensions, what you will find is C equal to 1. Okay. C is a number which roughly characterizes the number of degrees of freedom of the theory. Okay. Yeah. No, H is independent of C. This is just a commutator of the L's themselves. No. Okay. So let's now go to higher dimensions. If you look at this algebra, this commutator, what you find that there is a set of these generators where there is no central extension. If there is a central term in the algebra, what it really means, it's not really a symmetry. I mean, there's some problem with implementing the symmetry, some obstruction to implementing the symmetry. However, L minus 1, L0 and L plus 1, these form a closed algebra with no central extension, because this coefficient then vanishes. For m equal to 0 it vanishes, plus or minus 1 that vanishes, and you can see that you can never get out of this thing. So, this formed a closed algebra, and we showed, so this together with L minus 1 bar, L naught bar and L naught this bar, there are 6 generators, and we showed they can be grouped of translations, dilatations, rotations, and what I call special conformal transformation. There are 2 of those, there is 1 of those, there is 1 of those, and there are 2 of those. This accounts for 6. For D greater than or equal to 3, there is no analog of the Virasoro algebra for Mn all the way from minus infinity to plus infinity, but this is the thing that generalizes. So, let me write down what we call the conformal group in arbitrary dimensions. Conformal transformations. I'll call it P mu. They are given by the generators I del x mu, mu equal to 1 to D. These are translations. Then there are dilatations. Then there are rotations. And then there are special conformal transformations which are given by these differential operators, and every time there is an index, you should sum over the index. You can combine these things into some nice generators. So, define now, so combine then into a set of generators A and B. So, A runs from 0, minus 1 and 1 to D. So, there are D plus 2 of those indices, and they are defined as follows. So, they are antisymmetric matrix, antisymmetric operators, which so there are only not all of them, not D plus 2 whole square, but some number, and you can sort of painfully sit down, plug these things back in, and calculate the commutators of these things acting on functions, on ordinary functions, and you get an algebra which looks like this. There is no bracket here. Yeah, this is not a commutator, just a regular bracket, where is a diagonal matrix 1 1 1 minus 1. There are d plus 1 ones and there is 1 minus 1. If these G's were just the diagonal matrix 1 1 1 1 1 1 1, this would be the rotation group in d plus 2 dimensions. This is exactly the commutator of the angular momentum generators of the rotation group. This minus 1 spoils things a little bit in this commutation relations. So the rotation group in d plus 2 dimensions is OD plus 2. It keeps the bilinear form xi xa xb delta ab invariant. This transformation is called OD plus 1 comma 1. That comma 1 reminds you that there is a minus sign of that, which keeps xa xb gab invariant. So this algebra is the algebra of this I don't know what these groups are called. I mean, we call them OP comma Q. So those groups, and it actually, the algebra just actually lifts to a group as well. I mean, it's not just an algebra. In fact, for proper transformations, one requires things which have a determinant equal to 1, so it sticks in an S in front of it. So the SO d plus 1 comma 1. Okay? Good. This is just mathematics. I mean, I have just written down a set of transformations in arbitrary number of dimensions, which I called conformal transformations. I just took some linear combinations of the generators. The count has to be exactly the same. So let's count them. There are d of those. This one of those. There is d times d minus 1 by 2 of those, and there are d of those. And if you sum those things, you should get d plus 2 times d plus 1 divided by 2, which should be the number of antisymmetric objects where the indices run over d minus 2 digits. Okay. If there is a quantum field theory which is invariant under conformal transformations, this quantum field theory should have operators in the theory which implement these transformations, namely operators such that those operators commutators with the field gives rise to those answers, exactly like I did this capital L's. So let's now play a game. So for d equal to 2, SO3 comma 1 has 6 generators, which are the L0, L minus 1 and L plus 1 and L0 bar, L bar 1 and L bar minus 1. Okay. if I have a rotation group which is SOD, I can think of the rotation group as the symmetry group of a d minus 1 dimensional sphere. Like if you have the rotation group O3, an element of rotation takes a point on the 2-dimensional sphere to another point of the 2-dimensional sphere. That is what rotation does. Just does not change, does not go inside the sphere or anything like that. So, this is what I will call isometries. Isometries are, roughly speaking, symmetries which keep the metric on the sphere the same of a d minus 1 dimensional sphere. A d minus 1 dimensional sphere can be represented in d Euclidean dimensions by an equation which is x1 square plus x2 square plus x3 square xd square equal to 1. I have taken the radius of the sphere to be 1, just as a circle can be represented as x square plus y square equal to 1. 2-dimensional sphere can be represented as x square plus y square plus z square equal to 1, generalizes the dimensions. So, SOD is a symmetry of this equation. Okay. If I want to write, for example, so let us take the example of a 2-dimensional sphere. So, that is given by the equation equal to 1, and if I want to figure out what is the formula for the distance between 2 points on a 2-dimensional sphere, okay, what I need to do is to so the 2-dimensional sphere is a thing like this. There is x3, there is x2, there is x1. So, I want to look at 2 points on the sphere given by x1, x2, x3 and x1 plus dx1 plus x2 plus dx2 and x3 plus dx3. So, what do I need to do? I want to calculate dx square equal to dx1 square plus dx2 square plus dx3 square, but always keeping this condition. Okay. That is a funny thing to do, because so might as well solve this condition. This condition means that x1, x2, x3 are not independent of each other. There are only 2 of them which can be taken to be independent. Fair enough, because a point on a 2-dimensional sphere is given by 2 numbers, the 2 angles theta and phi. So, why not do this? So, why not write the usual polar decomposition This is the standard coordinatization of a sphere in terms of the angles theta and phi. Plug this thing in, and what you of course get, which is the standard distance between the points theta and theta plus d theta and phi plus d phi. All this shows is that a curved space like a sphere can be thought as embedding in a flat space. This is like flat space. The fact that you have all these sine squared thetas and all that are signatures that the sphere is actually a curved space. So, you can think of this as a surface with codimension 1 in this case in flat space. This is the flat space, this is the equation which tells you that you restrict to those points. It is just a way of thinking about curved spaces. This is actually the way I think Gauss thought about curved spaces. That is how we discovered the Gaussian geometry is thought of it is in this way. Well, if this is the story for SOD, there must be a similar story for SOD comma 1. Why not? So if I write SOD plus 1 comma 1, I might ask, if I embed this in some kind of flat space, what kind of surface should I write on that flat space such that under the action of this I go from one point of the surface to another point of the surface, exactly as we did for the sphere. This can be, the action is represented on a surface which is given by the equations minus u square equal to minus 1. Whether it's a plus 1 or a minus 1 doesn't quite make a difference. I'll just tell you one of the cases where this can be done. This minus sign carries the signature of this comma 1, as we just showed, that there had got to be a minus sign in the distance which we were considering. And then if you write the metric as dx1 square plus dx2 square plus blah 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 minus du square, this is going to give you the distance between two infinitesimally close points on the surface which is defined by this. A generic name for such surface is called a hyperboloid. And what I have just described for you has a name. It's called anti-de Sitter space, Euclidean anti-de Sitter space. Is given exactly by these two equations. Okay, just as a sphere is given by the equations x1 cross square x2 square plus c square equal to 1, dx square equal to dx1 square plus dx2 square dx square. This is what the definition of the Euclidean anti-de Sitter space is. There is a, what is the dimensionality of this space? You had d plus 2 coordinates, you have one condition, so therefore there are d plus 1 independent coordinates. So this has a notation, it's called Euclidean for E for Euclidean, and looks like ADS d plus 1. Sometimes I'll just, for this lecture, I'll forget about the E, I'll just write ADS d plus 1. Okay. Now, yes, it's Euclidean because I will see why it's Euclidean, because once you solve this thing and put it back in here, the metric you find is an Euclidean metric with all plus signs in it. Do you have a minus here? Yes, even though you have a, if you want to get a Lorentzian metric, you have to think of two minus signs and one of them goes away. If the right hand side was a plus 1, you would have called it a de Sitter space. Okay. When I first started working in this subject and I wrote a paper which is anti-de Sitter, my wife asked me, why anti-de Sitter? So I said de Sitter was this guy, this great guy who wrote down this solution of Einstein equations with a cosmological constant. So Rita said, so he did something wrong, that's why it's called anti-de Sitter. No, he didn't do anything wrong, it was just, it's anti because of this one additional minus. So now you can see there could be an intimate connection between conformal field theories and something on anti-de Sitter space, because the symmetries of both these things are the same. It doesn't tell you that there has to be something like that, but it tells you there is a good chance that something like that might happen. Now, so let me proceed a little bit with the mathematics before I come to the physics aspect of it. Now, just as for a sphere, it's sort of useful to it's useful to write independent coordinates on the sphere, which are the angles. So you would imagine might as well use some parameterization of this x1, x2 and use so that this equation is automatically solved. There are of course many possible parameterizations corresponding to various different coordinates which you pick on this hyperboloid which is defined as the space. So I'll just give you one of them which is particularly insightful, and two of them I'll give. The first one is called a global coordinates, and they are given by two. So I'll give these examples for ADS3. So D equal to Q. So there should be ADS3 should have this 4 of these things. So x3 is just given by 10 nu goes sine phi. I think nu goes from 0 to pi upon 2 and then if you write down that metric, this is what you get. And if I write R equal to sine nu, then ds square becomes R equal to 10 nu. ds square becomes 1 plus r square dt square plus d nu square by 1 dr square by 1 plus r square plus r square d phi square sine square by cos square is r square. So that's correct. And this actually shows you something a little bit interesting. If you take this is an Euclidean space. I mean there is no time in here. Okay. Now suppose I take tau to I times t, this gives standard ADS3, Euclidean ADS3, which has bs square with a minus sign out here. And this tells you something interesting about this space. This is the only time I will talk about real time in these lectures. Now, in a curved space, you don't need to know much any general relativity to do this. In a flat space, if I had the distance between the invariant metric is say dx square plus dx square plus dy square plus dz square. This is of course in c equal to 1 units. So a light ray is given by equation if along the x direction is given by x equal to plus or minus t plus a constant. If you draw a picture with time and space starting at some point 0, this is light going to the right, this is light going to the left. That's a standard picture of a null cone. It has the feature that if and yz equal to constant. So light is light goes along trajectory such that dA square is equal to 0. So that's what happened, that's what I obtained by solving dx equal to plus or minus dt, and I got x equal to plus or minus t. Right? So this is just standard spatial relativity which you study. So that the same thing happens in a curved space. The light rays are still given by dA square equal to 0. So if I take radial light rays, they are given by the equation dr dt by 1 plus r square, and if you can integrate this, I'll leave it as an exercise. What you can show is the following. This Euclidean space sort of looks like this. It looks like a tin can, like a cylinder. This is the direction which is time. This is an angle which is phi that forms a circle, and this is the direction which I called r. Okay. R goes from 0 to infinity, but notice I haven't drawn a huge cylinder. R should go from 0 to infinity, right? It is a very fat cylinder. And the reason I didn't draw it as a fat cylinder, that even though R goes from 0 to infinity, if you ask what is the physical size of this thing, one way to measure the physical size is, one way people measure distances in astronomy is in terms of time. You say something is 4 light years away, that means light took 4 years to come, 2 hours, right? So you can measure distances by the time taken by light to go through the distance. You can integrate this equation and easily see that from any point in the interior, shoot a light out, it will reach that r equal to infinity in a finite time. The integral of this is a tan inverse. That's why it reaches in a finite time. So for all physical purposes, this is like a box. It's really like a tin can. And that's very essential to the physics in anti-de Sitter space. Okay? So this is my short excursion into real time. Let me come back to Euclidean time. Well, none of this is here. I just wanted to give you a little picture of what this is about. And let us keep this metric, and I'll write down another metric. So what I can do is the following. Suppose I want to know, I know this thing has a symmetry. The symmetry is O d plus 1 comma 1. I know what the generators of the symmetry are in terms of u, x1, x2 and x3. Right? So if I call this as x0, then the symmetry generators are x a del del xb minus xb del del xa. That's how I obtain the fact that it is a symmetry of this hyperboloid, where a and b runs from 0, 1, 2, 3, 4 of them. I am just describing ADS3 just for simplicity. This of course extend all the way to ADSD. Okay. So it must be true that if I substitute, make these changes of variable and plug it in and use the chain rule, I will get generators which involve nu or r, equivalently r, tau and phi, and del del r, del del tau and del del phi, right? And if I make changes of r, tau and phi according to those laws, plug it in into this dA square, that should remain exactly the same. It has to be. It's just change of variables, right? So let me give you the change of variables in another set of coordinates which will turn out to be very insightful. So these are called global coordinates. So let me write this in something which is called Poincare coordinates. And in this case, this distance between two neighboring points, the Poincare coordinates have coordinates which are denoted by t, y and z. There always has to be 3 of those, and they are given by 1 upon z square dt square plus dy square plus dz square. If you know this, you will recognize as the metric on the upper half plane if there were just 2 of those. And there is a formula which tells you how u, x1, x2, x3 are related to these 4 things. If you want, I can write them down. They are not very insightful. There is a certain formula which tells you how u, I mean, for example, they are a little bit complicated, which is why I didn't want to write it down. For example, u has to be written as 1 upon 2z 1 plus y square plus z square minus t square, or plus t square. And similarly, x1 is t. I might as well write them down. x2 is 1 upon 2z pretty complicated, sorry, y square plus z square divided by, no, it's just y upon z, I'm sorry, y square, yeah, y square. So again, you can use this change of variables, plug it into back in those generators and obtain all the generators of the group, which is now for radius 3, the group is O4, 1. No, radius 3, so it's O3, 1. Because d plus 1 is equal to 3, so d is equal to 2. So it's O3, 1. And I'll write them as, with this, the generators can be written as, now you introduce again complex coordinates as t plus y, sorry, t plus iy is equal to u, t minus iy equal to v, sorry, u bar, and then the generators are written as follows: plus half so this metric became, let me write down, sorry. So in terms of these things, these become 1 upon z square dz square plus du bar. And similarly, m0 bar, m minus bar and m plus bar with u replaced by u bar. This is just the answer. Now, these relations are actually rather suggestive. Now, what do these act on? They act on functions of t, u and u bar. Okay. So these act on functions t, u and u bar. But they can also act on fields t, u and u bar. And if you look at this metric, so in the Poincare metric, z equal to 0 is the boundary. This was the thing at r equal to infinity. So you suppose I have a function, I have a field in ADS3, and the behavior of that field as a function of u bar went as z raised to the power delta minus. So then you see what happens, dz delta minus times some function of u and u bar as z goes to 0. Suppose I have that. I haven't told you why I have that. Suppose I have that. Let's plug this thing back and see how do these generators act on this field near z equal to 0. Okay? Now see what happens. Let's look at M0. M0 of phi near z equal to 0, there is a term which is half z del del z. So acting on this thing, this will just gives delta minus times f. So m right, that's the first term, and the second term just remain the way it is, delta minus u del del u, and similarly m0 bar phi as z goes to 0 becomes, I can say that delta minus by 2, because they are a factor of 2, z to the delta minus f plus z to the delta minus u bar del del u. So that means that the sum of m let me remind you of the formula which I wrote down just a moment ago for transformation fields of fields in a two-dimensional conformal field theory of dimension h plus h bar. If you look at that formula, what you will find that L naught acting on that field is in fact h plus h bar acting on f plus plus the dilatation like x1 dd x1 plus x2 dd x2 acting on f. This seems to suggest that once I take out this factor z to the delta minus, I get a function, and the way the symmetries of this ADS space act on that field is exactly like two-dimensional conformal transformations of a field of conformal dimensions h plus h bar. You can do the similar thing for all the generators, and what you find is exactly each of these generators, when they act on a field very close to this boundary z equal to 0, they are just acting on conformal fields with the corresponding dimensions. So this tells you there must be an intimate connection between, just mathematically, just functions in ADS space with what happens to them near the boundary, take out this piece, and what happens there near the boundary, the action of symmetries are exactly the same as the action of the two-dimensional conformal group which acts on this function. Okay. There seems to be, yes. I use the fact without justification that this behaves like that near z equal to 0. Yeah, but of course, in reality you have to solve a wave equation, and if you solve the wave equation you find that it doesn't behave like that everywhere, it only behaves near the boundary.
I could see for the higher ones, for M plus, for example, you really drop.
I agree. You have to need that. Yeah, yeah. For the higher ones, you need that to put z equal to 0. For this one, you don't. You're absolutely right. But this asymptotic behavior is something which I assume, which I have to prove if I have a right theory. So the connection which this seems to be hinting at is the following. Is that there is a field in what I'll call bulk. By bulk means ADS3. There is a correspondence with an operator on the boundary. The field in the bulk is phi, roughly speaking, whatever the operator on the boundary. I'll fix what this operator or coupling or whatever on the boundary, some function on the boundary, which are related by similar symmetry transformations of the group. No physics so far. This is just mathematics. So let me now come to the physical reason why such a thing could be true. Pure algebra, that's why it's just mathematics. Okay. Why would such a thing? So this is consistent with a conjecture that a quantum field theory on the boundary is somehow related with some theory in the bulk. Whether this theory is a classical field theory or quantum field theory depends on parameters, but there is a connection between these theories, and there seems to be something very intimately tied with the symmetries of the theory. What the ADS-CFT conjecture tells you is the following, that a conformal field theory plus deformations, which makes it non-conformal in d dimensions, these all Euclidean, is equivalent to a theory which contains gravity. And the reason why gravity comes into the picture is a bit involved. It has got to do with string theories and all kind. I don't want to go into all that, but there's some theory which contains gravity. There is reason why that theory should contain gravity and nothing else in d plus 1 dimensional in plus deformation. This is the conjecture. I will not tell you the physics which led to this conjecture. It's a long and beautiful story of how this came about. This has got to do with the physics of Hawking radiation, of black holes, and various kinds of things. But I tell you the underpinning which actually led to this, and the underpinning was actually large N theories which we considered. In our discussion of the large N limit an important thing we learned is that at large n is equivalent to some classical theory of the singlet fields. Where the h bar of this theory is like 1 upon n. And I gave you one example of such an explicit member of such a correspondence, where you had quantum mechanics. Quantum mechanics is a name plus 0 plus 1 dimensional theory, because it has no space and one time, and we found that it is equivalent to a 1 plus 1 dimensional theory. Somehow the dimensionality of the space on which this classical theory of singlet fields lives is always larger than what he started off with. Something just grew out of nowhere. Of course, it couldn't come out of nowhere. You might think having a one extra dimension means an one extra infinitely worth degrees of freedom. Where did those come from? They came from that infinite number of degrees of freedom which were hidden in that matrix. They sort of got cleverly reorganized into a dimension. That's the magic. What this is telling you is, in fact, this is a concrete realization of higher dimensional examples of this, where the quantum field theory on the boundary is typically a large n theory, and this would be the singlet sector theory. And the boundary is two dimensional. So that's what this is all about. And in fact, the way this conjecture was arrived at was precisely making a very deep connection with large n gauge theories, black holes and Hawking radiation, which all sort of brought together into this nice little package which came to ADS-CFT. So I'll finish you by indicating two concrete calculations. I will not do the details of the calculations, but I hope to tell you enough of them, which tells you what to do with this. What do I do with such a thing like that? It's a conjecture. There is no proof for that conjecture, but there are lots and lots and lots of evidences for that conjecture coming from a large class of field theories. So for the moment, let's assume that the conjecture is correct. A conjecture is mostly useful when it is not proven, because once it is proven, you know everything about it, so you don't learn anything new. So let's assume that the conjecture is there and see if we can learn anything new. So one of the things we should be able to show is that if I calculate something in the bulk in ADS3, it should correspond to well recognized things on the conformal field theory which lives on the boundary. Okay? And one of the best recognized things in conformal field theory on the boundary are correlation functions. So let's see, what should I do in the bulk to calculate correlation functions of the conformal field theory on the boundary? And this is the prescription. You have a bulk, and there I'll do everything in the context of ADS3. The whole thing just generalizes to any ADS without much trouble, but this is a little bit concrete. So bulk has coordinate z, t and y, or equivalently or z, u and u bar. I will assume in the bulk there are fields like a scalar field which is a function of z, u and u bar. there is a metric, there could be a gauge field G, U and U bar, and so on and so forth. So, the claim is that for each of these fields in the bulk, there is a one-to-one correspondence with an operator on the boundary, and the operator on the boundary I will call O, U and U bar. Just by the symmetry structure, this has to be a scalar under rotations of the two-dimensional space O, U and U bar. This has a correspondence with some vector current in fact on the bulk, and sorry, not this. This has a correspondence with the vector current in the bulk, and this is particularly interesting. It corresponds to a fundamental quantity of any quantum field theory called the energy momentum tensor. I mean, it's quite natural because the energy momentum tensor is the response of a theory by changes of the metric tensor. What you are supposed to do is is to calculate the path integral. In principle, you are supposed to calculate the path integral over all these fields d phi, dg mu nu, dA mu. This is the bulk path integral exponential to some bulk action, and the claim is this is equivalent to some degrees of freedom which I will generically write as some large n degrees of freedom with some action, typically for example a matrix model you can have. However, there is a problem. The problem is that first of all, we do not know how to integrate over metrics, we do not know how to do quantum gravity in this fashion. So, that is a problem, let us ignore that for the moment. But the thing is that this is supposed to be, all these fields are supposed to live on this space which has a boundary. I have to give you some boundary condition, otherwise this thing does not make any sense, right. So, I have to specify some boundary condition. So, I have to write here with the condition that phi 0 u and u bar. So, phi z u and u bar goes to z to the minus f times say phi 0 of u and u bar, and similarly for a mu and g mu mu. Because it is only for things like this I have shown this correspondence of these generators. I will come to that why the behavior is like that. So, you get an answer on the left hand side which depends on a set of functions which are defined on the boundary. This does not have anything like that, there is no set of functions on that. So, you have to tell me what that is. What it turns out is that the conjecture is that this is equal to times some operator of u and u bar. This is this operator. Okay. If you are feeling uncanny about it, let me give you the concrete, a very concrete example of this. A concrete example happens in ADS 5. So, for concrete example, bulk is string theory on ADS 5. This contains a scalar field, metric and 10 to the 10,000 other fields in it. I am not going to be writing them down. It is of course a string theory, it has like billions and billions of things on it. I do not even want to care about what those are. The boundary theory is a very well known gauge theory. It's an SUN gauge theory, pure Yang-Mills theory, with 16 supersymmetries. So what knows what this symmetry is? Okay. So this integral in that case is like integral dA mu, and there are some other supersymmetric partners of those, and then there is an action which looks like 1/4 trace f mu nu. This is the standard E square minus B square for a gauge field, and the connection is that this scalar field is called a dilaton. The dilaton corresponds to that operator trace f mu nu, trace f mu nu. So what this means here is that you write down times some function of the boundary fields and then trace f mu nu. Similarly, the metric is dual to the energy momentum tensor, which you can write down. There is a one-to-one correspondence which is entirely almost determined by the supersymmetries of the theory. But for that it's not very important. I am just trying to give you a brief sort of description of what one would do with this. So I'll erase this for the moment. We don't want to talk about supersymmetric gauge theories. Operator on the boundary. And the operator on the boundary I'll call O, U and U bar. Just by the symmetry structure, this has to be a scalar under rotations of the two-dimensional space, O, U and U bar. This has a correspondence with some vector current, in fact, on the bulk, and sorry, not this. This has a correspondence with the vector current in the bulk, and this is particularly interesting. It corresponds to a fundamental quantity of any quantum field theory called the energy momentum tensor. I mean, it's quite natural because the energy momentum tensor is the response of a theory by changes of the metric tensor. What you are supposed to do is is to calculate the path integral. In principle, you are supposed to calculate the path integral over all these fields d phi, dg mu nu, dA mu. This is the bulk path integral, exponential to some bulk action, and the claim is this is equivalent to some degrees of freedom which I will generically write as some large n degrees of freedom with some action, typically for example a matrix model you can have. However, there is a problem. The problem is that first of all, we don't know how to integrate over metrics. We don't know how to do quantum gravity in this fashion. So that's a problem. Let's ignore that for the moment. But the thing is that this is supposed to be, all these fields are supposed to live on this space which has a boundary. I have to give you some boundary condition, otherwise this thing doesn't make any sense, right? So I have to specify some boundary condition. So I have to write here with the condition that phi 0 u and u bar, so phi z u and u bar goes to z to the minus f times say phi 0 of u and u bar, and similarly for a mu and g mu mu. Because it is only for things like this I have shown this correspondence of these generators. I will come to that why the behavior is like that. So you get an answer on the left hand side which depends on a set of functions which are defined on the boundary. This doesn't have anything like that. There is no set of functions on that. So you have to tell me what that is. What it turns out is that the conjecture is that this is equal to times some operator of u and u bar. This is this operator. Okay. If you are feeling uncanny about it, let me give you the concrete, a very concrete example of this. A concrete example happens in ADS 5. So, for concrete example, bulk is string theory on ADS 5. This contains a scalar field, metric, and 10 to the 10,000 other fields in it. I am not going to be writing them down. It's of course a string theory. It has like billions and billions of things on it. I don't even want to care about what those are. The boundary theory is a very well known gauge theory. It's an SUN gauge theory, pure Yang-Mills theory with 16 supersymmetries. So what knows what this symmetry is? Okay. So this integral in that case is like integral dA mu, and there are some other supersymmetric partners of those, and then there is an action which looks like 1/4 trace f mu nu. This is the standard E square minus B square for a gauge field, and the connection is that this scalar field is called a dilaton. The dilaton corresponds to that operator trace f mu nu, trace f mu nu. So what this means here is that you write down times some function of the boundary fields and then trace f mu nu. Similarly, the metric is dual to the energy momentum tensor, which you can write down. There is a one-to-one correspondence which is entirely almost determined by the supersymmetries of the theory. But for that it's not very important. I am just trying to give you a brief sort of description of what one would do with this. So I'll erase this for the moment. You don't want to talk about supersymmetric gauge theories. Okay. Now, most of the time this is not very useful because one doesn't know how to calculate the left hand side. Neither does one know how to calculate the right hand side. So what is going on? There is some situations which actually happens in this ADS 5 string theory duality. There is some regime of parameters where it so happens that the left hand side can be very well approximated by a classical answer. That means so this is the special case which is very useful, is that the bulk is approximately classical. So what this means that in that case I can just erase that functional integral and say that I obtain the classical action on the space of classical configurations where the classical configurations satisfy the boundary condition This is the kind of action which one deals with in Hamilton-Jacobi theory. In Hamilton-Jacobi theory, like take a free particle, right? I mean, if I take a free particle, like the action is given by from T1 to T2, dt like half x dot square, I put m equal to 1, and I have to tell you So if I want to, the classical equation of motion is satisfied by x2 minus x1 by t2 minus t1 times t plus x of 0. So you can plug this thing back in here and obtain what that action is. The action is a function of t1, t2, x1 and x2, right, by taking various derivatives of these action as a function of x1, x2, t1 and t2, you get a set of equations which are called the Hamilton-Jacobi equations. Okay. The Hamilton-Jacobi equation is a complete reformulation of standard Newton's laws for such actions and for more complicated action. It's in the same spirit. You calculate the action. What can the action depend on? Action as an integral over all space. It can only depend on the boundary conditions. And that's why it's a function. It's actually a function of these boundary conditions phi naught. This is a function of phi naught. This, you don't know anything. You know, there's some theory, highly quantum, you have to really do the functional integral, but it's also a functional of this boundary, this function phi naught and u of e naught. But this tells you something interesting. If this is correct, then what I should be able to do is the following. I should be able to take del phi naught of u and u bar on both sides, right. On the left hand side, it gives you e to the minus s classical del s classical del phi naught of u bar. I can do e to the s classical times this operation. Then this thing goes away, and that becomes just the expectation value of the operator u bar. And you can take two derivatives of this, d square du phi del phi 0 u prime u bar prime. So that gives you del phi 0 u bar del phi 0 u prime u bar prime. This gives a 2-point correlation function. If I set this to phi 0 equal to 0, phi 0 equal to 0, this gives the 2-point correlation functions of the theory defined by this. And the theory defined by this has to be a conformal field theory, because on the left hand side, if the boundary conditions were not non-trivial, it sort of destroys the full conformal symmetry. So putting the boundary condition to 0 restores the conformal symmetry, so that it should be a conformal field theory. So this is the procedure. Suppose you don't know a very strongly coupled theory for which you don't know how to calculate these correlation functions. If this correspondence is correct, all you have to do is a classical calculation. How do you obtain a classical action? How did you obtain the classical action in this case? You first solve the equations of motion, and then you substituted the equations of motion. So the answer for this, I think, is something like x2 minus x1 whole square divided by 2 t2 minus t1, and you substituted that with the given boundary conditions at t equal to t1, x equal to x1, t equal to t2, x equal to x2, and you obtain the action as a function of this boundary condition. So you have to solve a classical equation of motion, substitute that into the action, and the answer becomes a function of the boundary condition. Same thing here. Whatever action you have, the action is typically an action of Einstein-Hilbert action for gravity plus scalar fields or what have you. Solve the equations of motion and substitute that back into the action, and you should find an answer which only depends on the boundary condition. Take derivatives of whatever answer you get, and you get the correlation functions of the original conformal field theory. So this thing, I'll just give you the answers for these things for a simple example. It's actually a bit quite involved. cutoff ADS space has the same metric, but Z goes from epsilon to infinity rather than from 0 to infinity. So what I have done is, if the ADS space is in these coordinates, there is a boundary of ADS space which looks like this at Z equal to 0. I have taken this thing a little bit inside and put in a cutoff. And then I have to be a little bit careful about a factor here which I have to put, which is epsilon to the minus delta minus. This just follows just from dimensional analysis that there has to be a factor like that. But then looking at this, you sort of immediately figure out that epsilon is an ultraviolet cutoff in the field theory. And the reason is actually quite fundamental, why it should be an ultraviolet cutoff in the field theory. Z plus u bar del u bar. So that tells you that if I scale u and u bar by the same amount and also scale Z by the same amount, then that's a symmetry of the theory, right. So a scale transformation on the boundary must be equivalent to a scale transformation of Z. A scale transformation on Z means actually changing Z by an amount proportional to Z. Okay. Now let us look at this thing. So I said that by looking at delta minus, it looks like that this object has a dimension delta minus. So what this thing does is to restore this thing by having epsilon to the power minus delta minus restores the dimension of this. This is pretty much like that if you have in a some field theory like we were doing, like d dx some phi to the power 4, and this u, that coefficient u, is really a dimensionless number raised to the power some cutoff raised to the power 4 minus d, or raised to the, and then or a raised to the power d minus 4, where a is the lattice spacing in position space. So we get the picture that as we whatever we call the cutoff boundary of the ADS spaces, as we move closer and closer to the real boundary, we are going to the limit when the position space cutoff is going closer and closer to 0. Just like going to the ultraviolet, that is a continuum limit, and as I go more and more into the interior, I should go more and more into the infrared. This is something called the UV-IR correspondence. Okay. Having done that, let me just outline in 2 minutes how a calculation is really done. So I will give you an 10 minutes, right, 5 plus 5. I do not have much time to do denormalization, I will just mention the physical thing. So a calculation. in ADS D plus 1. And the bulk action is going to be a scalar action epsilon to infinity d diameter. These are the boundary coordinates, this is like the u and u bar. And then there is a metric of the area space, and then I put in a mass. Suppose this is the bulk action. So how am I going to calculate this thing which I call the classical action on a classical configuration? So first I have to solve the equation of motion. Phi equal to 0. I'll just write down what the solution is. You can sort of explicitly write down the solution at z and x. The one set of solutions is like integral of phi k, like phi. Let me write the solution in momentum space. I can, so the metric is these had the y and t or whatever I had before, right? But since there is a translation invariance in x going to x plus constant is a symmetry of the theory. So then I can Fourier transform in that x direction. So I'll write down what that solution is. This turns out to be of the form some Bessel function of kz. Where nu is a quantity which turns out to be, doesn't matter what this thing is, okay, what the form of this thing. All this says is that I have ensured that when z is equal to epsilon, it is a function phi naught of k, because they just cancel with each other. But if you now look at this thing and obtain near z going to 0, what you will find is that there is a this k mu has two terms. One goes as z to the nu, the other goes as z to the minus nu for small values of z. So you are going to get two terms which are z to the z plus 2 plus nu, and another set of terms z to the by 2 minus nu. And all I need to show you that it is indeed true that functions like this for large z become some power of z and then some function. Okay. So you can just sit down as an exercise, take this solution, plug this back into the action. You will find pretty much like that particle case an action which is a function of phi naught of k, and I'll write down what that answer eventually is. So that answer these are the Fourier, these are that phi naught of k I have written down, and then and where h of k is some coefficient which depends on mu times k to the power 2 nu. This one little thing I wanted to point it out in this, as epsilon goes to 0, this thing diverges, right? You think what's going on? How do I get a divergent answer? Or even if I keep epsilon finite, you get a cutoff dependent answer. But we just learned that in quantum field theory you always get that. If you just sit down and calculate something, you always get something which are cutoff dependent. And then what you really got to do is to renormalize the theory, and in your way of thinking, renormalizing the theory is to sort of go down to all the way to low energies, in which case you keep accumulating terms in the action, which and the renormalized action, the final answer should be finite. So the cheap way of doing that is to use what are called counter terms, which get rid of things like this, and you get a finite answer which is essentially given by phi naught h of k, from which you can calculate O of k, O of minus k is given by some k to the 2 nu. It's a power of k in position space, it will be a power of x, and if you calculate what the power of x is, you find 1 upon x raised to the power 2 delta minus delta plus, where delta plus is d by 2 plus mu. I've just given you the answer, it's a long calculation, so I didn't want to do this calculation. So this just explicitly demonstrates that this prescription indeed leads to scale invariant correlation functions in the theory, and that the whole thing can be extended to higher point correlation functions. Large n. This was a calculation in the bulk. So it's an I've assumed that inequality, that there is a large n theory. So what really happens is that for those cases where you know both the left hand side and the right hand side, you can independently calculate the right hand side in the field theory. In this case, a large n Young-Mills theory at n equal to 4. You can do this calculation. Most of the time in a strongly coupled theory, you cannot do a calculation. But if you have billions of supersymmetries, you can do it for arbitrarily strong coupling. So you know what the answer is, you know, do this calculation, and then you check, you exactly get the same answer. So that's the check of this correspondence. It's not a proof, but it's a check. But then we, as I said, conjecture is useful when it is not proven. So then we just use this. They said, okay, it looks like to be true, so what can we gain out of it? So in the last 5 minutes, I'll finish this course of lectures by indicating to you what is the meaning of renormalization group in this entire context in the bulk theory. And the way it happens is as follows. So I have motivated for you screen at z equal to epsilon rather than going all the way to z equal to 0. What that somehow should correspond to is a quantum field theory which is living on this, which has not a lattice spacing but some position space cutoff, which is epsilon. So therefore, I should be able to do this entire Wilsonian process of lowering the momentum space cutoff or increasing the position space cutoff. So that should correspond to this in taking this screen and moving bit by bit into the interior. Now I also told you that in this classical limit, the classical action was on the right hand side some large n theory, I don't know what it is about, but the important thing of this classical action with phi going to z to the delta minus phi 0 was up to some epsilon to the power minus phi 0 times some operator. Okay, so phi 0 was a function of the boundary coordinates x or u bar. So this is the phi 0 of u and u bar times some operator. Okay, now things which appear in a quantum field theory action in front of operators are called couplings. That's why mass is a coupling, phi 4 whatever appears there is a coupling. In this case, the coupling is also space dependent. It's not a big deal, it's generalized notion of a coupling. Okay, because in terms of the eigen operators of the RG, it will have lots and lots of terms, but who cares? It's still a coupling, right? So boundary conditions correspond to couplings of this deformed conformal field theory, some quantum field theory. So boundary conditions corresponds to couplings. Okay, so now I can do the following operation. So therefore it seems to suggest that if I was considering one theory in the bulk which has a cutoff at z equal to epsilon, and consider another theory which is in the bulk where z was equal to epsilon by 2, the same physics would correspond to some boundary conditions phi naught here and some boundary conditions phi naught prime here, and just by doing a bulk calculation I should be able to relate phi naught prime to phi naught, and that would tell you in the quantum field theory how a coupling at cutoff epsilon is related to a coupling at cutoff epsilon upon 2 or epsilon 2 times epsilon or something 2 times epsilon, because they are actually going inside. So this is the idea. Okay. So more precisely what needs to be done is something like this. I will just give you one more one more things. So define an object is, after all I am writing classical action, but it was an approximation to a path integral after all in the bulk. So it is a bulk path integral with phi at epsilon x equal to phi naught of x, some d phi e to the minus s of phi. But I can, where s of phi is a thing which has an integral of z from epsilon to infinity, integral over the other coordinates times some Lagrangian. So let us write this thing as psi. I call it a psi because being a path integral with some specified boundary condition, it satisfies some kind of Schrodinger equation. That is what Feynman showed. It satisfies the Schrodinger equation with a Hamiltonian which comes from this action, okay, except that you have to be a little bit careful because these are Euclidean actions. Okay, so I can write this thing now. So this is the notation. The notation just tells you that I have area space in a box at z equal to epsilon. I calculate the path integral with this boundary condition, I call that psi. So clearly I can write an identity in the following way. Let me first write down what the identity is. This is the law of superposition of quantum mechanics. So what I mean by this expression is as follows. By using areas theory is going to be some path in this is the conformal field theory plus phi prime of L, because that is at the boundary conditions. So look at the psi IR, it is phi prime of x, sorry, phi prime of x times the operator of x. And psi uv is something which I in principle am able to calculate by just calculating the classical action and just putting in the right boundary conditions. Psi uv will be some functionals of these things. This object is also of course something like a wave function, so it satisfies an equation. So psi uv has, like you think of this direction as a time. It is not really a time, it is Euclidean space, anything you can call it a time. So it satisfies an equation for very specific cases where this calculation can be precisely done, and one of the cases are cases which are similar to the linear sigma model which I discussed earlier. It's a property of a general class of field theories which are called double trace deformations. You can explicitly verify you get exactly the right beta function this way. One more comment, and I finish with this comment, is that of course the whole thing is very useful in the classical limit. right? Otherwise you don't know how to do all these functional integrals there. But in the classical limit, we know what happens to this equation. This equation becomes a Hamilton-Jacobi equation. So it becomes an equation which is something like del S del L plus H equal to 0. So it's a Hamilton-Jacobi equation, and that del L will sit there, which becomes a renormalization group change of the couplings. It's a first order derivative respectively. When you apply the same thing for gravity, what happens is you can sort of re-massage these kind of Hamilton-Jacobi equations into equations which are called Raychaudhuri equations, which tell you the how a bundle of geodesics converge or diverge under the action of this geometry. So that establishes a connection to those equations and renormalization equations of a putative dual quantum field theory. So this is what I mean by geometrizing the renormalization group. You can think of really doing the renormalization group on the quantum field theory by integrating out chunks of bulk in the bulk, and the equations, these are equations of motion, essentially follow from equations of motion of the bulk fields as they propagate in Z, carry the information of how coupling changes with the change of cutoff on the boundary theory. Okay, that's all I can tell you at the moment. Thank you very much.